in 10.2, we're going to conduct a hypothesis test here, but this one's from data. So you can see I have all these 7-Up cans, and I want to see whether the machine's working right. So I have all the amounts of milliliters that are in there. So the first thing I'm going to do is go to Stat, Edit, clear out the old, and type in the new. I'll be right back. Hold on one sec. Poof! Magically, they're all there. Okay, so in this particular problem, I know what the standard deviation should be, I believe. Let me scroll down for a second. There, I'm back. My computer is being possessed there. Okay, so what they want to know is there sufficient evidence to change these hypotheses? So let's see here. Reject the null hypothesis, excuse me. So we know that the mean should be 355 if the machines are working correctly. Then the alternative, she's worried that it's miscalibrated. Go ahead and read the problem from the notes if you're interested. But that would be that it's not 355, right? Could be underfilling, could be overfilling, etc. So that's the null and alternative hypothesis. Alpha, they're setting up as 0.05 again. So alpha is right here. So we need the test statistic and all that jazz. Okay. Well, we're going to get that out of the calculator when we do the test. So I've got the data in here. I'm going to go to Stat, go to the right to Tests, pick number 1. I'm allowed to do number 1 because see that right there is sigma. I can do a test for the mean when sigma is known. That's a z-test. Okay, so I pick number 1. This is data, so go to the left to press enter because I typed in all that information in list 1. My mu0 is 355. Enter. My sigma, not alpha, don't get those confused, sigma was 3.2. L1 is where I typed the data in at. Frequency, just leave it as 1. Mu0 mu is not equal to mu0. I want a two-tailed test. So I'm going to go press enter on this one to make it dark. Then I'm going to go down to calculate and press enter. There I can see the test statistic, which is z equals 2.7083. Now again, you're not allowed to get away with just writing that. When you're in the class, you're going to have to write out how you get it and all that jazz. The p-value, they tell us, is 0.0067. That's the probability in both tails. What it does is it takes z is positive 2.7083 and negative 2.7083, and then it figures out the area in the tails past both of those values. Okay, so it's both tails put together. The calculator already knows it's both tails. That's why you picked a two-tailed test. You can see it right up here with the not equal sign. It knows what it's doing. Okay, so the p-value is 0.0067, which is for surely less than alpha, right? Which is the 0.05. Therefore, we reject H naught. If you want to do it the classical way, which you would have to do in the next one, it's the next page, but right down there. Okay, so but I'm going to put it right here just for the sake of argument. So the classical method, steps 1, 2, and 3 are the same, right? But what the difference is that we need critical values. So you're saying, look, if alpha is 0.05 and this is a two-tailed test, that means that what I really need is alpha over 2 for my critical values. So alpha over 2 would be alpha divided by 2, which is 0.05 divided by 2, which is 0.025. That's the area in the left tail for the classical method. So then you do inverse norm 0.025, enter. And you can see that the critical value is plus or minus 1.9599. i.e. 1.96. So if you're past 1.96, but we are, our test statistic is 2.7, right? 2.7 standard deviations away from the mean. And we're saying, look, anything past 1.9599 standard deviations away from the mean, we're going to reject. Since 2.708 is greater than this, we reject. All right, all done with that. I'll see you for the next section.